So yeah, today I'm going to talk to you about hyperdoctrines, and as far as the technical material goes, there's not going to be anything novel. I think I'm going to catch you up to where the technical state of the art as of like 40 or 50 years ago. But the goal is to sort of present this material in a way that makes it friendly to the audience I'm talking to right now. Because I think hyperdoctrines are a useful tool, and I think philosophical logicians could get a lot out of using hyperdoctrines, but their theory is not often presented in a way that would be accessible to most philosophical logicians, or that shows any reasons why philosophical logicians might care. So that's kind of the aim. Just some acknowledgements. This is joint work with my colleague Graham, who is present. So if you ask really, really hard questions, I'm probably just going to punt them to Graham. And if you find errors, they're probably mine and not his. We got super useful feedback from Sean Standifer. He's incredibly good at getting useful feedback. I meant this as a nice thing to say. It occurs to me that this might mean like lots of people go ask Sean for feedback, and that might be mean to him. But I meant it as a nice thing, so there you go. Okay, some introductory stuff. Some of the details of the particular system I'm going to present here are going to seem ad hoc, and I just want to flag that up front. And a lot of the times when things seem ad hoc, it's because they in fact are. But since my goal here is to give a presentation that's simultaneously sort of self-contained and pretty simple, that's kind of what led to some of the ad-hoc-ery. And so all of the almost all the ad-hoc-ery you're going to see is a result of that aim, that I want to simultaneously be fairly simple, but also self-contained, get all the information kind of in one spot. And to accomplish that, I did just end up having to sort of, to sacrifice a little bit of naturality here and there. And so sorry about that, but I hope that serving this goal is worthwhile. So I'm going to do a really big picture, and then I'll do just a big picture, and then we'll get into some details. So really big picture, we're doing algebraic logic when we're doing hyperdoctrines. And so, and in particular, we're doing categorial logic. So we're going to be doing a little category theory. And so the sort of thing to have in mind is Lindenbaum algebras. They are to propositional logic as hyperdoctrines are to predicate logic. And so there's a sense in which what we're giving here is an alternative to model theoretic semantics. Okay, so that should help kind of situate it a little bit. Now, a little closer in, not the very big picture, just the big picture. We're going to work in a polyadic first order language, but without identity. And we're going to augment that language with an incredibly mild typing system that I'm going to go through in detail. The types and terms in the resulting language are going to form a category. And we're eventually going to call that category B for base. Interpretations, the type of interpretations we're going to look at, are functors that map this category B to algebras. And then if you want to capture different logics, you just use different algebras. And all the choices you have to make there are the choices you'd expect. And so there's a modularity to the hyperdoctrine system, or to the hyperdoctrine framework, that's really pleasant. Okay, so that's the picture. Now to some details. Since I said we're going to be working in a slightly idiosyncratic language, this polyadic first order language with a little typing, I'm going to go through the details of this language. And I'm going to go through it in like some excruciating detail. So every expression in the language we're going to build has two parts, an untyped part and a typing part. And the untyped part, like you would expect, is just I think, can people see my writing here? No response.
Yeah, we can see it.
Great. All right, so the untyped part's a sequence of symbols, just like you would expect from a formula. The typing part over here is just a set of variables. And intuitively, it's the set of variables you're regarding as free in the untyped part. Okay, now, in order for that to make sense, every variable that in fact occurs free in the untyped part has to also occur in the typing part, because the typing part has all the variables you regard as free, and you should certainly regard as free all the things that in fact are free. So here's an example. Suppose we had this formula over here, Rx1, x2. X1 and x2 are variables, let's suppose, and they occur freely there. So they're both going to have to occur over here in the typing part. because the typing part contains all the things that we regard as free. X1 and X2, in fact, are free, so we will regard them as free. But not every variable that occurs in the typing part has a free occurrence in the untyped part, or has to have a free occurrence in the untyped part. So for example, we're going to allow something like this, where this X3 here, we're regarding it as occurring free, even though it doesn't occur at all in the untyped part. Okay? And so this X3 here is something like a dummy variable. Whoops, dummy is spelled with 2 M's. But the dummy variables are actually going to play a pretty important role in the system. So even though they're dummies, you should pay attention to them. All right. So that was kind of an overview on the syntax. I'll just get really concrete for a little while here. The vocabulary is going to have countably many variables, countably many constants, some separator symbols. The set braces are there because we have sets on the typing parts of all of our expressions. We have countably many predicates, a bunch of connectives, and one quantifier. I'll occasionally talk about intuitionistic logic, and when I do that, you'll have to implicitly assume that we've extended our language so we have both a universal and an existential quantifier. It's a logic talk, so someone's probably going to ask what happens if we have uncountably many of one of these things. I have no idea. I don't know if anything interesting at all hinges on that. At this point, I have no reason to care about it, but if there's a reason I should care about it, you should tell me. So it's a pretty standard batch of vocabulary. This is how we construct our terms. I said every well-formed expression is going to have an untyped part and a typing part, and that includes our terms. Okay. So every constant counts as a term where we have to say what counts as free, and in a constant, we don't have to regard anything as occurring free because it's a constant. Every variable counts as a term, but we have to specify that it's occurring free in itself because it is. And we're going to allow terms of higher arities. So we're going to allow what would normally be considered just a sequence of terms to count as a single term. So you give me a term and another term, I can paste them together. This is extremely useful because it allows us to treat all of our predicates, no matter their arity, as if they're unary from a technical perspective, and that streamlines a lot of the presentation. When we combine terms like that, the things we regarded as free are unioned up on the right-hand side there. And then we have this version of what we call maybe syntactic weakening here. That's just me underlining it. It's not supposed to say anything. So syntactic weakening just says, you give me a term, you can regard more variables as occurring free in it if you want to. Okay, so there's not much excitement on the term side, and there's also not much excitement when it comes to formulas. The one thing worth noting, if you give me a predicate and then you fill it up with a term, the typing part of the term comes along into the formula. Okay, so every formula is also typed, every formula has a typing part, and they sort of inherits it from the terms and the atoms, and then as you move up, you just sort of keep everything at one level. So I'm allowed to combine things from the same level using the connectives in the expected ways. Okay, we also have syntactic weakening here. It struck me several times that perhaps we could get by with just one syntactic weakening, either at the term level or the formula level. But it's nice to have both around, so I put them both around, and maybe we need them both. I don't know. Nothing hinges much on whether we can get by with less. And then there's a unique way of removing degrees of freedom, or removing variables that count as free, and that's quantifying. This makes it look, just the way this reads, it makes it look like we don't allow vacuous quantification, but in fact we do, right? You could take something where y doesn't occur at all, let's say, and then you could say, hey, let's treat y like it occurs free. And then you could quantify out that y. And so this would be like vacuous quantification. It's just to get vacuous quantification in the construction procedure, you have this extra little step. Okay. So that's the, I think that's everything there is to say about the grammar. So what we're going to do is show how to regard the types and terms in this language as a category. And so our goal at the moment is to find some natural way to view the terms in our language as arrows in a category. And you might initially wonder, like, why would you do that? Why would you regard perfectly you know, terms that never did you any harm, why would you regard them as arrows in some category? And the answer is when you look at terms in the right way, especially terms in this language, they kind of scream at you that they are arrows in some category. So if you look at the typing part of a term, the right-hand side, it kind of tells you how many name-shaped gaps there are in the term. And then if you look at the untyped part over there, it's a list of name-shaped things. And if you were to fill in the gaps over here with name-shaped things, well, that would just be like doing some kind of substitution. And so it would spit out, after you perform that substitution, a different list of name-shaped things. And so you can see how this term kind of yells at you like, hey, if you give me a bunch of things to fill all these gaps, I will spit out a list of name-shaped things for you. And so that's sort of the idea to have in mind as we're constructing this category, is roughly speaking, we read the right-hand side of a term, the typing part, as a domain, and we read the left-hand side as a codomain. It tells us what this thing's going to spit out. Okay, so that kind of leaves us with two questions. First is, when should composition be defined? Well, if this over here is the codomain of that term, and this over here is the domain of that term, in order for composition to be defined, those two things have to match, right? The arrows have to be properly aligned before you can compose them. And so that gives us an answer. That composition should be defined when the cardinality of x and the length of sigma are the same thing. When there are just as many gaps in tau bar x as sigma provides us in sigma bar y. Okay. Okay, so given that that's when we ought to have the composition be defined, what should the composition be? And our idea was that this composition is just going to be substitution. So we're going to take all of the x's, and we have to take them in some order because the sigmas are given in a particular order. And we're going to do a simultaneous substitution. And the natural ordering to choose is we're just going to take the x's in their subscript order. And so I write this x with a line over the top of it for the x's in their subscript order. And so the way composition is going to work is like this. You just take all the x's and you swap them out for what sigma gives you. And then you notice that the typing part from sort of the inside term comes along for the ride. So just by looking at terms and thinking like, well, what does this term yell at me? Well, we see that it has gaps and that we can fill those gaps. And if we do fill those gaps, there's a certain way that we can get another list of things out. By taking that seriously, this is kind of what is forced on us. Let's look at a few examples just so we can kind of make that a little more concrete. So here are two terms that ought to compose because I have just as many things here as I have there. Okay, and if I were to do the composition, let's change colors here because, you know, that makes things fun. What we said we would do is we would pair up the things I'm getting here with the stuff I have there. And so what I should do is take this x1, pair it up with x3, take this a3, pair it up with x4, do that substitution to x3. Well, that doesn't get me much excitement, right? I'm just taking the x3 and replacing it by x1. And then the typing part of the inside thing comes along for the ride. So what I ought to get here is this. And now I'm going to turn the page and I'll see if I did that correctly. Yes, I did. That's nice. Okay, so that's how the composition ought to work. Let's look at a few more examples because there's a couple interesting phenomena that we should make sure we understand. If I were to have instead had over here the term x4, bar x3, x4, instead of getting the first thing here, I would be getting the second thing. And so what I ought to get this time is something like a3 bar x1, x2. Because I just do the pairing like we did before. Kind of missed there, but that's okay. I do that pairing, and then I do that substitution that pairing suggests on the thing I have over here. And the result should be a3, and then the typing part here comes along for the ride. Okay. Now, of course, we can have complex terms. Okay, I did that correctly. We can have complex terms like x3, x4. We regard that as a single term. And now if I do this composition, I basically get what you would expect. You know, the x3 gives me x1. We already saw that. The x4 is going to give me a3. And so what I should have here is something like, let's see, x1, a3. I think, yeah, x1, a3, bar x1, x2. And so that, you notice something if you look at this closely. It looks like this term is sort of behaving like an identity on the left. Okay, keep that piece in mind. If we were to switch the order there, so we had x4, x3 rather than x3, x4, it no longer behaves like an identity. This is going to be a flip-flopper operation. It's a technical term. Instead of giving me x1, a3, which is what I started with, it now gives me a3, x1. Okay, so that's how the composition works. Hopefully that's enough examples to kind of solidify the idea. There's an immediate problem. We're trying to build a category. We're not just trying to give some random way of combining terms. We want to actually build a category. The categories have to have identity arrows. And we saw that this x3, x4 guy kind of behaved like an identity on the left. x1, x2 is going to behave like an identity on the left as well. Because they both behave as identities on the left, neither behaves as an identity on the right. And so we can see that x3, x4 behaves like an identity on the left. And so this top line is going to give me x1, x2, bar x1, x2. You can also just do the computation if you want. You just pair things up like we've seen already, and that's what you'll get. And so notice that when I compose with x1, x2 on the right, I don't get back the thing on the left. So this is not behaving like an identity arrow. Same down below. Since x1, x2 behaves like an identity on the left, this is going to give me x3, x4, bar x3, x4. And so that just means x3, x4 isn't behaving like an identity on the right. So neither of these behaves like an identity on the right. They will both behave like identities on the left. But in categories, you need genuine identities, genuine two-sided identities. Those were our only candidate identity arrows. Neither of them worked. But each of them took us to one of the candidate identity arrows when we composed with things on the right. And so our solution or our workaround to get identity arrows is let's just treat all of these candidate identity arrows like they're one arrow. Right? So that is, let's work with an equivalence class of terms rather than with individual terms. How should the equivalence go? Well, let's think what we do want. We want those two things to both be the same arrow so that we actually have a genuine two-sided identity. We do want that. We crucially do not want those two things to be the same, right? Because we already saw that this here, it does not act like an identity arrow on the left. It acts like the flip-flopper, the thing that tells you to switch the order of stuff. Okay, and so it might initially seem like it's going to be tricky to figure out exactly what the equivalence relation is going to be. It turns out it's not that bad. There's a very natural equivalence relation to use. And what you do is you just do these simultaneous substitutions, but where you always preserve ordering while you do it. So I take the x's in their subscript order, replace them with the y's in their subscript order, where I'm assuming here that x and y have the same cardinality. And that gives us an equivalent term. This kind of substitution will always be monotonic. And I guess I should say what I mean by that. If you give me I less than j, and then you ask what does xi go to and what does xj go to, if xi were to go to say like xk and xj went to say xl, then k would be less than l. Things that are earlier in the subscript ordering get mapped to things that are earlier in the subscript ordering, and things that are later in the subscript ordering get mapped to things that are later in the subscript ordering. And so this prevents us from doing that flip-flopping that we wanted to avoid. Turn the page, there we go. And so the idea here, our goal is to build this category where the terms are arrows. And what we see now is that actually our terms should be, our arrows should be equivalence classes of terms, not individual terms. Okay, so I did a bunch of I had a whole bunch of category words in there. And so for folks who don't do a lot of category theory, you can get pretty confused at this point. What the hell's going on? Remember, the plan is we're gonna find a way to view the terms in our language as arrows in some category. Okay, that's the plan. to do that, it turned out we needed to work with equivalence classes of terms, because otherwise we didn't have identity arrows. Okay, and this was the equivalence relation you're going to use. This, where you can do these changes of variables, but you do the changes so that you always preserve the ordering of the variables. Now, of course, categories also have objects, so we know what our arrows are, and now we want to know what our objects are. And the idea is the way we're going to figure out what the objects are is by just looking at the identity arrows. Because you could, if you wanted to, present categories without objects. You just have to use the identity arrows. And in any event, the identity arrows naturally each correspond to one particular object. So now that we know what our identity arrows are, we should be able to figure out what the objects in this category should be. So that's the end of our little interlude. Okay, so the identity arrows, they were the things that looked like this. All of our candidates had that form, and if you just see how things like that behave, they all behave like an identity arrow. So what we have here is you give me a set of variables, and you take them in their order over here. That's what our identity arrows look like. If you give me any two sets that have the same cardinality, then both of these terms are going to be in the same equivalence class, and all of the terms in that equivalence classes, that whole equivalence class will behave as an identity arrow. And so what we see is that the identity arrows in our category naturally biject with the cardinalities of the typing parts of the terms. And because of the formation rules, all of those are finite. And so the objects in our category, we're going to call them types. And there's one of them for each finite number, I guess I could say, but each natural number n. And we're going to call that type Tn. And in essence, it's just the type of expressions that have n gaps in them, n holes in them. Okay, so the category we've constructed has for its objects types. The types are essentially just n-gapped expressions. So there's a type of zero-gapped expressions, which you might call sentences, and there's going to be a type of one-gapped expressions, which have one hole to be filled in, and so on. The arrows in this category are terms, or equivalence classes of terms, as it turns out. We're going to call that category B for base category. We're going to use pointy brackets to talk about equivalence classes. As a result of the way the equivalence relation works, every single expression, every term, and then later every formula is going to have a representative where this is the typing part. And so it's convenient to have a name for that set. And so that's, where this is the typing part. And so we're going to use x1n as a name for the set of variables x1 through xn, the first n variables. Okay, now that was all syntax, and so now we're going to actually be moving to doing some logic stuff. I have to make a choice about where to do that. I could try to do it in general, but it would be really hard. And so in the remainder, I'm just going to focus on like the Boolean or classical case. Now, we have the base category, and I told you that interpretations are going to be functors that map that up to algebras. I could, at this point, just present things as like, here's what type of functor we're interested in. Here's what a hyperdoctrine is. But it would be very unclear why we focused on things that had those particular features. And so what I'm going to do is something slightly unusual in order. I'm going to essentially do the construction at the heart of our completeness proof. I'm going to build what you might think of as like the canonical hyperdoctrine or the canonical model. And by looking at its features, we'll see what features hyperdoctrines in general ought to have. Okay, so the idea is that we're going to map every type to the algebra of formulas that have that type. So we're going to send every type Tn to the algebra of formulas whose typing part has cardinality n. Of course, I didn't tell you anything about what the algebra of formulas is, and so we should say words about that. But the answer is it's just the Lindenbaum algebra modified to keep track of typing and type equivalence. That's all. So let's see what we mean. So define the turnstile however you usually do. Whatever your preferred way of defining the turnstile is, proof theoretically, axiomatically, it's not terribly important. You just need to add one condition, a condition that says you can prove this change of variables version of phi from phi. And you can do that whenever all the appropriate free for things happen. So here you have a big simultaneous substitution. And so you want to make sure that you're always substituting for X something that is free for that X. Okay, and provided that's what you're doing, you say that this is an allowable change of variables, you just add that one extra condition, and then otherwise you define the turn style however you usually do. And then from there, things work out as you expect. We say formulas are equivalent when they're equiprovable. I'm going to use pointing brackets for the equivalence classes here as well. And then the algebras we're interested in are those algebras that have equivalence classes as objects. They're ordered by the turn style, and they have operations induced by the connectives in the expected ways. Okay, so this really is just the Lindenbaum algebra with a tiny modification to keep track of the typing, but even that modification is sort of the expected sort. Again, you could be very lost at this point. So let's just remind ourselves the plan. We're trying to build a particular hyperdoctrine, the syntactic hyperdoctrine. It's sort of the hyperdoctrine you'd expect to find at the heart of a completeness proof. It's like a canonical model. It's going to be a functor that maps our base category to algebras. Remember that functors have two parts. They map objects to objects. They map arrows to arrows. We've seen how the functor should behave on objects. It sends every type to the algebra of formulas of that type. What we need to do is see what it does to arrows. And arrows in the base category are equivalence classes of terms. So we need to see what this functor should do to equivalence classes of terms. Okay, let's look. So suppose we're in this situation. We've got the type T2 and the type T3, and we're looking at them, and there's some arrow in between them. I know what my functor does to T2. It sends me to the algebra of formulas with typing part having cardinality 2, and I know what it does to T3. It does something similar. What I don't know is what it does to the arrow. Well, let's get even more concrete. Let's suppose we're looking at this particular arrow, the arrow that corresponds to that equivalence class of terms. Okay, and I want to think, like, what should that do to formulas? Well, if you gave me a formula over here in T3 land, a formula that has sort of 3 gaps in it, there would be a natural thing to do to it, because this term supplies me with 3 things that I can use to fill such gaps. And if I were to do that, if I were to in fact fill those gaps with what this term gives me, I would end up over here. I would end up at this formula. And the things I would be regarding as free are these things, because that's what the term told me was regarding as free. We would be regarding as free. And so what I see is that this arrow going from left to right on the bottom seems to correspond to an arrow going from right to left on top. So that's what we're going to say the functor does. This functor maps the arrow from left to right on the bottom to the arrow from right to left on top. And so what we have here is a contravariant functor, right? Okay, but it arose pretty naturally by just thinking about these things and the way they behave and the way substitution ought to work. Now, there's a formal definition, and the formal definition is a little ugly. You might look at this for a while and wonder what the hell's going on, because I don't just take these taus here and directly substitute them into the phi's. I have to do this extra rigmarole with the z thing. And why is that there? It is well defined, I promise. You can check that. It's required because of free for fiddliness. Just little details that you have to get right to do the free for business. You're always substituting in for a variable something that is free for that variable. I'll give you an example of the kind of fiddliness that we're trying to work around here. Let's suppose we were trying to do this substitution. Okay, so remember, this here is a Boolean algebra homomorphism. It's the Boolean algebra homomorphism attached to this term, this equivalence class of terms in here. Okay, and now I'm saying, what will it do if I apply it to that equivalence class of formulas? So the naive answer would be, well, I just take this x1 and plug it in for the one thing I have free over here, cool, and I end up down in this spot. But that's clearly incorrect. We don't want things to behave that way, because I took something that had a free occurrence of a variable, and now it's bound. And so it ought to be the case that when I do a substitution, I bind things, right? This is the free for business that we're trying to work around. Okay, so the naive answer doesn't work. Slightly less, okay, so it's red because it doesn't work. Slightly less naive answer. Well, maybe what I need to do is just switch to a new variable. And so maybe what I think is like, well, I'm just going to use this thing, because surely that is something I could use instead. And then if I did that substitution, you know, I would take this x3 and I would plug it in for x2, and this is where I'd end up. Well, it turns out that that's not right either. And the big problem is that these two terms aren't actually in the same equivalence class. Because to do an equivalence, the equivalence relation we're interested in, you do a simultaneous substitution for all of these variables, and it's always going to be monotonic. And so since x1 is the first variable you have over here, you're going to replace x1 with something that occurs the first thing down here. We didn't do that. So those two things aren't in the same equivalence class, so the slightly less naive answer is still incorrect. So the correct answer is to just do what we said on the previous slide. You do the substitution for all new variables. You do that, you apply that substitution to x1. You see what you get. So in this case, you're going to get x3, but note our typing part is x3, x4, not x2, x3 like we had before. After you do the substitution, you end up here at this equivalence class. And that is the same as this equivalence class. So you should compare these two, the slightly less naive answer and the correct answer, and that'll give you a good sense for what's happening here. Okay. So all of that to say, yes, there's a little fiddliness we have to deal with, but you can see why we need to deal with it, and it's not too bad at the end of the day. All right. Now, the algebras have operations corresponding to connectives. We've seen how terms behave. We haven't seen anything about quantifiers. How are quantifiers going to be captured? Well, it turns out before we look at quantifiers, we should look at something else. We should look at these rather boring looking maps. So suppose y is not in x. I'm going to write that up here. And then it's going to go away as soon as I turn the page, but there it is for the moment. This term maps to a fairly boring homomorphism. So if we think about how it behaves, what I'm going to do is I'm going to take these in order and replace them with this. That's the same thing. So I'm not going to change anything in phi. And then the typing part here is going to come along for the ride. And so I just end up there. So there's a sense in which these terms, the homomorphism corresponding to these terms are inclusions. Okay, neat. Super duper surprising fact. If I were Dave Ripley at this point, I would have like the galaxy brain exploding picture in the slides. You can define quantifiers by how they relate to these inclusions. And I think that's incredibly surprising. So let's see how that pans out. Here's just something that looks mildly scary, but isn't. Here I have the inclusion, and I apply it to phi bar x. When I do that, I'll end up at phi bar x comma y. We already saw that. But note that for phi bar x to make sense, I'm still supposing y is not in x. Y can't occur free in phi. If y occurred free in phi, then it would have to occur in the typing part. But y is not in x, so y doesn't occur in the typing part. Okay. So this whole thing proves that just if y doesn't occur free in x, and this proves that. But if phi proves psi and y doesn't occur free in phi, well, then your usual universal introduction rule tells you that, in fact, phi proves the universal version of psi. Okay, and so that's interesting, Shay, but why do we care? Let's adopt some abbreviations real quick. We're just going to use this j hat notation for the term that omits the jth x. Okay, so it just skips over the jth x and grabs all the rest of them. We're going to write pi nj for this universal quantifier map that goes on the things that have n free things, the formulas that have n free variables. Okay. What we just saw on the previous slide was that if I apply this homomorphism to that class of formulas, and I'm less than this class of formulas, that happens if and only if the class of formulas I applied the homomorphism to is less than or equal to pi applied to the other class of homomorphisms. And this is exactly what it takes in this category, in this setting, for the pi to be a right adjoint to the substitution map. So quantification is adjoint to inclusion. Universal quantification is right adjoint to the inclusion. And you can work through the details. Existential quantification is left adjoint to the inclusion. And so once we know what terms are, it tells us how what the homomorphisms are that the terms attach to. It tells us what quantification ought to be like by just looking at the adjoints. And so for those who don't do a lot of category theory, once you can say something's an adjoint, that really does mean it's well understood and we know what's going on. So let's take a look. What have we learned so far? Well, what we've learned is that there's a natural categorial structure hidden inside this predicate language we looked at. It's a fairly normal predicate language with a mild typing system added on top. There's also a natural contravariant functor that sends each of the types in that category to an algebra of formulas. And then it does something interesting with the terms and maps them to substitutions that go in the opposite directions, contravariant functor. And once you have all that on hand, quantifiers just show up as adjoints to the inclusions. Okay, that's what we've learned. There's a couple additional facts worth mentioning. They again look kind of scary, but they aren't. Remember, this pi thing is our universal quantifier map. All this here is extensional confinement, that if you have phi here and xj doesn't occur free in it, but you're quantifying at xj, then that quantifier can jump across the disjunction, right? So this is just extensional confinement. Substitution and quantification also commute. If I were to quantify and then substitute for everything that was still free, that would be the same as if I substituted for all those same variables and then quantified. So you can see that in a concrete case. Here I can quantify the x2 away and then do some substitution at the variables that are still free. Might end up here. I could also substitute for those same variables, x1 and x3, just do some substituting. And then I just got to quantify out that middle zone. If I follow this map explicitly, I'm going to end up at this part. But these are clearly the same equivalence class of formulas. Okay, different representatives of the same equivalence class. Cool. So those are just some other facts about how all of this algebraic machinery that we've inherited from our logic interact. All right, and there's how it works in general. It looks ugly, but it's the same phenomena we just noticed on the previous slide, just made totally general. Neat. So that's the syntactic hyperdoctrine. It's the hyperdoctrine you construct at the core of your completeness proof if you need a completeness proof. And now I want to build hyperdoctrines in general. And so the idea is, what I'm going to do is I'm just going to define a class of objects and interpretations that capture the essential features of the syntactic hyperdoctrine, because it was fairly natural. And then if I do that correctly, I should get a completeness proof immediately. Hopefully that works. And if we also have something that's sound, then we're onto something. And so spoiler alert, yes, in fact, we do get something sound. Neat. So let's actually try to think through how that should go. So I want to capture the essential features of the syntactic hyperdoctrine. And so what I want is a contravariant functor, okay, because the syntactic hyperdoctrine was a contravariant functor. And I want it to generally behave like the syntactic hyperdoctrine behaved. Okay, so what was that like? Well, it's a contravariant functor. It mapped to these particular Boolean algebras. We're going to allow a little more freedom. It's going to say it has to go to arbitrary Boolean algebras. And then the homomorphism for these substitution homomorphisms, we're just going to choose arbitrary Boolean algebra homomorphisms. And then instead of explicitly mentioning the quantification map, we're just going to have the adjoints to the inclusions. Okay, and so concretely, here's the actual definition of a Boolean hyperdoctrine. It's a contravariant functor from the base category to here. This is the category of posets. If you're wondering why it's not just the category of Boolean algebras, you can ask about it in the Q&A. It's a contravariant functor to the category of posets whose image is in the category of Boolean algebras, so that all of these intuitively inclusion maps have adjoints. And then that we have this extensional confinement feature. and substitution and quantification intuitively commute. Okay, that's the actual definition of a Boolean hyperdoctrine. Now I need to think about how to interpret our language in an arbitrary Boolean hyperdoctrine. And it's not terribly hard to see how we should do it. If you give me something n-ary, so something that has n free things, it should map to some object in the n free things algebra. Okay, so it just maps to something in whatever your hyperdoctrine associates to the type of n free things. And then from there, things take off and just work out inductively. So this is going to be a homomorphism of Boolean algebras with the appropriate domain so that it can attach to something like this. And so we just see where it goes. And that's where our atomic formula is going to map to. Little t, like trivial truth or whatever, it maps to the top of each algebra. The negation, since everything's a Boolean algebra, it just maps to the complementation operation in your Boolean algebra. Conjunction maps to meet, and I could go on, but I'm not going to. Universal quantification, if you've quantified out your jth formula, then you just apply this jth adjoint. So this is just the adjoint to the j hat bar x1 through xn term. Whatever your hyperdoctrine does to that, it has an adjoint. That's required by the definition of the hyperdoctrine. That's what this is. It's just the adjoint to that, the right adjoint. Okay, cool. That's how interpretations work. We define validity as always goes to the top, no matter what. That's to be expected. And now I'm going to do 4 metatheory slides altogether. So here's my completeness proof on the first slide. Fact 1, the syntactic hyperdoctrine is in fact a hyperdoctrine. That's to be expected. We defined hyperdoctrines to be things that look like the syntactic hyperdoctrine. Fact 2 is the identity interpretation, the thing that essentially maps every predicate to just itself. This is basically just R. That interpretation is an interpretation. And on the identity interpretation, every formula gets mapped to its own equivalence class. Fact 4 is that something is in the equivalence class of the trivial truth just if it's a theorem. You put those things together, you get something that's not a theorem, then it's not valid because it won't turn out to be at the top in the syntactic hyperdoctrine. End of completeness proof. The lesson to take from it is that since we just cooked things up so that the syntactic hyperdoctrine was a hyperdoctrine, and so that the identity interpretation was an interpretation, completeness just falls out. Soundness is just a very straightforward induction on the length of the proof. I think soundness is quite surprising despite the fact that its proof is very straightforward. If you think about it, the syntactic hyperdoctrine was a very unusual, among the class of hyperdoctrines, the syntactic hyperdoctrine is very unusual. So for example, every algebra that the syntactic hyperdoctrine maps to is a countably infinite Boolean algebra with countably many atoms. In an arbitrary hyperdoctrine, we might be picking out finite Boolean algebras. That's quite different, right? So we've allowed a great deal more freedom. Nonetheless, we don't falsify anything new. We falsified all the non-theorems in the syntactic hyperdoctrine, and we don't end up falsifying any theorems by adding all this extra freedom. I think that's pretty surprising, and it suggests that the hyperdoctrine semantics is formulated in a fruitful way. And then the 4th metatheory slide just generalizes to other settings. With very minor changes, all you have to do is change algebras, and you get the same result for other logics. So for example, if you wanted to do intuitionistic logic, you would just use hating algebras. And then in your definition of a hyperdoctrine, you would have to force, in addition to right adjoints, to have left adjoints to interpret the existential quantifier. If you wanted to do FDE, rather than using Boolean algebras, you just use De Morgan lattices. If you want to do R, rather than using Boolean algebras, you use De Morgan monoids. And then you have to deal a little bit with this extra confinement axiom. Right? You don't just have extensional confinement, you have intentional confinement, which you have to add as a condition on your hyperdoctrines. But otherwise, there's this very uniform treatment of a broad range of logics. So what we've seen overall is that after adding just an extremely minor amount of typing to an ordinary predicate language, there's a pretty natural categorial structure that just sort of pops out. When we take that categorial structure seriously and try to see how it corresponds in a category theoretic sense to our logic, we see this contravariant functor that kind of pops up. And if we just take contravariant functors of that sort as our semantic objects, we end up in hyperdoctrine land. We're just doing hyperdoctrines at that point. And when we mimic all the constructions, not just the construction of the syntactic hyperdoctrine, but the construction of how we interpret things in the syntactic hyperdoctrine, we end up with a semantics that is in fact sound and complete. Okay. So I take it if you're a mathematical logician and you learn, and this is the first time you're seeing this, you might think that it's cool, but you might, whether you're a mathematical logician or a philosophical logician, wonder why you should care about this. Well, I'll give you a variety of reasons to care. The first couple reasons are essentially mathematical. This allows all the flexibility of the categorical setting, and that's advantageous. So for example, if for some reason you think sets are problematic, but you don't think, say, like the category of categories is problematic, I don't know why you would think that, but suppose you thought that. Well, the category of posets is just part of the category of categories. And so since everything here is just taking place in the category of posets, it allows you the flexibility to ignore sets and just live in the category of posets, which you might think of as part of the category of categories. So maybe that's a type of flexibility that can get you somewhere. Regardless of that, of whether that particular example of why you might care doesn't or helps you, the idea is that category theory gives you a certain type of flexibility, and we've imported that here. Another essentially mathematical reason is this uniform treatment of a broad range of classical and non-classical logics, including both fully structural logics like classical and intuitionistic. Someone's probably gonna give me crap about calling intuitionistic fully structural. Okay, fine. And substructural logics. And people even looked at this in the case of the Lambic calculus and extremely substructural settings, not something like R. Those are mathematical reasons. Metaphysical reasons. The semantics that hyperdoctrines present you with give a very different view on the relationship between propositions and other items, other semantic items. So in particular, if you think about model theoretic semantics, right, terms denote objects, and the objects are kind of the base level of the semantics. They're like your semantic primitives, right? Predicates are determined, are interpreted as sets of objects, right? And everything else kind of gets built up from there. The bottom level is the objects. Hyperdoctrine semantics flips that completely. The basic objects are propositions. Those are sort of the primitive elements, right? The propositions are organized into algebras, and then homomorphisms between those algebras are the things that are the objects. Those are the things that are denoted by terms, right? And so you define the objects by how they relate to other more primitive elements instead of the other way around. And so that could appeal to certain types of metaphysicians. Now is where I get to the part of the talk so I'm going to go from like reasons you might care that are fairly out there to a little more concrete, but it's still, I'm still being pretty speculative here about like a way you might apply hyperdoctrine, the hyperdoctrine technology to help you out. So at the heart of the Neologis's project is this metaontological problem. And I think hyperdoctrines offer you an interesting perspective on that metaontological problem. So here's a little primer on neologicism for the unfamiliar. This will really just give you a taste. It won't get you very far. Neologicists take sentences like this one. This is called Hume's principle. Neologicists take sentences like Hume's principle very seriously. And so what Hume's principle tells you is that if you give me two second order variables, if you give me two concepts, they get attached to the same cardinal number just if there's a bijection between them. So I'm using some abbreviations here, this hashtag, if you will, octothorpe, that's the word. The octothorpe, it's a term forming operator that binds second order variables. Yes, I know there's discussion about whether that's exactly correct. It's good enough for now. And this semi-q symbol is an abbreviation for the purely second order logical formula. It says there's a bijection between the x's and y's. And so Hume's principle says two concepts get the same number. Two concepts are equinumerous just if there's a bijection between them. Now, Frege's theorem is that from Hume's principle, you can prove using second order logic. Well, Hume's principle entails, in a second order setting, all the axioms of second order piano arithmetic. So in words, arithmetic, second order piano arithmetic, is just Hume's principle plus second order logic with full comprehension. So Crispin Wright tells us this is exciting for the following reason. If second order consequence is indeed a species of logical consequence, the analyticity of Hume's principle ensures the analyticity of arithmetic. So that's a big deal. There's a problem. At the heart of neologicism is this meta-ontological issue. The left-hand side of Hume's principle looks like it's existentially loaded. The right-hand side doesn't look like it's existentially loaded. It feels like, if that's correct, if in fact we're reading our existential commitments off of the left-hand side and the right-hand side in like a broadly Quinean way, then it seems like it shouldn't be analytic. Hume's principle ought not be analytic. Why? Because you shouldn't be able to sit in your armchair, reflect on the right-hand side of Hume's principle, which has no commitment to objects, and come to find, in fact, that there are infinitely many things in the world, as the left-hand side guarantees. Right? You shouldn't be able to infer the existence of infinitely many objects just by reflection from your armchair. This is sort of the reason why we feel like Hume's principle ought not be analytic. Let's think about what the hyperdoctrine perspective tells us on this. From the hyperdoctrinal perspective, objects are just morphisms of a certain sort. And so when I'm asking the question, do the right sorts of objects exist? What that question becomes is, do the right morphisms exist? Are there appropriate morphisms between these algebras? But whether there's a morphism between some algebras is a question that concerns the structure of the algebras, right? It is just, you just have to look at the structure of the algebras, and a lot of times you can look at just the structure of one of the algebras, and that'll tell you what kind of morphisms there are going to be coming out of it. And so if that's correct, it gives you a reason to think that reflection on the right-hand side of Hume's principle, which will tell you things about the truths in a certain part of the image of this hyperdoctrine, may well tell you what kind of homomorphisms you have around. And once you know what homomorphisms you have around, you know what objects there are. Okay, so this is a speculative application of the hyperdoctrine semantics that I think, I mean, it's promising. Maybe it doesn't pan out, but it's a promising novel perspective on this metaontological thing that's been at the heart of neologicism for a long time. And in a sense, it gives a thin objects or content recarving picture, but in a new categorial setting. Okay, so I think that's all the actual material I needed to cover. If you decided that hyperdoctrines are your jam, here's some useful references that you could look at. And thanks so much. If you want to continue doing supergroup stuff, there's the website. You can also email me or contact me on Twitter. I'm done.